Okay. So for this problem, we are looking at stereochemistry. And so we can kind of get closer here. And like I said before, just to reemphasize, the way that we assign priorities is by, who gets to the highest priority atom or the highest atomic number atom first. So we're looking at stereocenter A at this point. We know that there is a hydrogen here in the back. So that's good. It's where it belongs. No issues there. And now we just have to kind of assign priority. And we know that the hydrogen is going to be number 4. And then we run into carbons at each point here. Okay, so that means we just need to take it a step further. Okay, when we branch out here, we just run into more carbons. When we branch out here, we run into a nitrogen. That's pretty impressive. When we run out when we take it a step further, on the top carbon here, we run into 2 oxygens. Okay, so as we know, oxygen has a higher atomic number than nitrogen, and so this top region is going to be first priority. Okay, but nitrogen is still better than carbon, and so this is going to be this direction is going to be third priority, and that second priority, and then that leaves this one to be third. When we connect 1, 2, and 3, we are going in the clockwise position, so it's going to be R. So A will have R stereochemistry configuration. Okay. So let me know if there's any questions on that. And we'll look at B. Sorry, I need to set up something. For B, we assume that there's a hydrogen here because carbon needs 4 bonds, and this one's going to be wedged, which means we're going to need to flip it at the end. So we start out with nitrogen as our first priority, and then hydrogen is our 4th priority. And then we end up with 2 carbons here, and so we need to branch out again. When we branch out here, we eventually reach an oxygen. Well, if we keep branching out here, we're just going to keep reaching more carbons, right? And that's not really interesting. So if we branch up, that's going to be the higher priority at number 2. This will be 3rd priority. So if we connect all of the numbers 1, 2, and 3, we get S, okay? But remember that our hydrogen is not in the back where it's supposed to be. So we're going to turn this into R, and that'll be our final answer. Okay, so B then will be R as well. And so C will be the answer for that one. Okay, stop me if you have any questions. Okay, so for number 2, where does the hydrogen have to be? To be in the back. What do you mean by that? So it needs to be dashed. And so in this case, it is wedged. And that means it's coming toward us. It's coming toward us out of the plane of the paper. While the dashed is going into the paper, it's going, within the paper. So we want that hydrogen to be dashed instead. What do we do to solve that problem? We just switch S to R or R to S. In this case, we got S, so our final answer will be R. Okay, for number 2, the way to attack these problems is always to draw them out. So we have our orange carbon here, which I'm going to represent here. And then I'll draw in another color. In purple is going to be our back carbon. And that will have these substituents here. So In black, I'm going to write the bond you're not able to see. And then in purple will be the open circle. And just to answer your question, Mallory, how do we know to draw the hydrogen in wedged instead of dashed? So in this case, there cannot be two dashed objects coming off of a carbon. For every carbon, there needs to be something dashed or wedged, or in this case, neither. You can't have two dashed, nor can you have two wedged. So the only alternative here is to have it wedged. So hopefully that makes sense, Mallory. Okay, so jumping back to number 2, we have our purple carbon and our orange carbon. So off of our orange carbon, we have a bromine, we have a methyl, and a hydrogen. Off of our purple carbon, we have a propyl group. So 1, 2, 3 carbons, and then an ethyl group, 1, 2, and a hydrogen. So this is really, really ugly molecule, and I don't know how to interpret this. So what I always like to do, I draw it once, I draw it twice, okay? So then I can easily see what's going on, name it. So when I draw my line notation, I exclude the hydrogens. So okay, and then it's saying how many stereocenters are there. So again, stereocenters are places where there are 4 individual distinct bonds. Here I see 2 stereocenters. There's going to be one here. There's a hydrogen here as well. There's going to be one here and one here. Okay, so where do I see that? So here's one distinct group. Here's one distinct group, another, and this whole thing is one group altogether. So that's 4 things. On the other hand, on the right stereocenter, there's 1, 2, and then this whole thing here, 3, and then a hydrogen. That's 4 distinct things once again. So the answer here is 2 stereocenters. Okay, any questions on this one? Okay. And then for number 3, we're talking about elementary steps and rate laws. So here, all you need to do is figure out what the rate law is from our steps, step 1, 2, and 3. And all you need to know here is what the what the slow step is saying. So you can pretty much ignore everything else. And then you take the reactants here, okay? And the one that matches that is A here, okay? Any questions on this? Okay. For number 4, we have a chair structure, and we have to identify the position of the ethyl group. So this is kind of like call it as it is. What is this ethyl group? What kind of position is this ethyl group in? So this one is in equatorial and it's facing up, okay? So imagine this is the plane, and this ring here is within the plane, okay? And let's imagine like a tree, okay? This is the plane, and then here are the roots, okay? Anything below, like these are below, these are like the roots, okay? And then everything above here is simply above the surface, like where the tree is, okay? So that's kind of how to visualize this. So this equatorial is slanted up, right? So it's equatorial up. All right. Any questions on this one? Okay. For number 5, So basically, we need to find the Arrhenius factor. There's only 2 equations we know that have the Arrhenius factor in them. And this time we're going to use that long one that kind of looks like this. Okay, this is the Arrhenius factor here. Okay, and we have every variable we need pretty much, and then we can solve for A. So K here, we're given is 34. This entire thing here, which is considered the slope, because this is kind of a y equals mx plus b format, is going to be, this whole thing is going to be negative 1.0784. And then the temperature is 343. And that allows us to just simply solve for the Arrhenius factor, okay? And eventually you're going to have some number equals ln of a. And to get rid of that, as we know, we're going to do everything e power, so we can solve for a at the end, okay? And if anybody wants, I can definitely walk through the algebra of that, and your final answer should be 1.2 E15. Is the moon outside? I have to see. Okay, hopefully, Kevin, hopefully it'll stay. Like, hopefully it's just in the horizon. But the horizon is the best part, isn't it? I'll have a look after. Okay. So, okay, let me know if there's any questions on number 5, and I can walk through the math if you guys want. For number 6, we are determining the rate law again, but it's a little bit complicated this time because of the fast equilibrium here. Okay, so we have fast equilibrium, and we know that by the double arrows, and we have a slow step following it right after. So therefore, what we can do here is relate the first and second steps together. All I'm going to do is cross these off here, okay? And then our final rate law would be considering this, this, and this, because we've connected the first and second reactions here, the first and second steps. And so our rates would equal K times A squared B. It's kind of like additive, right? We have 2 A's here. Okay, so this one would be D. Any questions on this? Is the last on fast equilibrium 2? It doesn't matter. This we can disregard because the fast step, the fast equilibrium has to be before the slow step, okay? Anything after the slow step, we can disregard, yeah. So the fast equilibrium has to be on top. Okay. 7 is more conceptual and a little bit hypothetical. So the first statement is saying that O2 is a reactant of this reaction. And in no place is it a reactant. It's only a product. And so this is false. B is saying that HO2 is a catalyst, which means that it is consumed and then reproduced at the end. So let's see. We see it here and over here. In reality, it's actually an intermediate, not a catalyst, because it was produced and then consumed again, which is the opposite of what we want for a catalyst. Okay. OH is an intermediate, so that means it's going to be produced and then consumed. And in that case, we do see that happening. So that is true. For D, If step 3 was the slow step, then the reaction is overall third order. Okay. So that would not be true. So let's take a look at step 3 here. If step 3 was the slow step, that would be the rate determining step. And we only have 2 reactants here. And so it will not be, it will not be third order, only second order. So that's wrong. And then E is saying if step 1 was the rate determining step, then the reaction would be first order. And that is true. If we only considered step 1, there's only one reactant, and so then it would be first order. Okay, so the answers there are C and E. Any questions on this one? Okay, so for number 8, we have a graph this time, and we have to determine the rate law with these steps. So we notice that step 3 is the RDS, the rate determining step, the slow step. But if we notice here, by the way, anything that's not a slow step, automatically fast. And we notice that it has double arrows, which means it's equilibrium, which means we can relate step 2 and step 3. If we notice there's an intermediate there, so we can cross that off, and then our reaction becomes, our simplified reaction becomes B to C, which means that B is the only rate determining reactant we have. So our rate will be, will look like this. Any questions on this one? For number 9, we have to use our experimental data to see what's happening with the rate law. And okay, so we'll use the isolation method. And in experiments, this is 1, 2, 3. In experiments 2 and 3, A stays the same, but B doubles, and we see a double in the rate. So that means this is going to be, B is going to be first order somewhere. And A in experiments 1 and 2 can determine if it affects the rate, and it does. It also doubles the rate here. Okay, and Megan is asking, does it not matter that B is also an intermediate? It does not matter, right? We can only cross off intermediates like we did there if there's fast equilibrium. Yeah. Okay. So for number 9, we see what our rate should be, our rate law should be. And there are actually multiple ways to get this because we have our fast equilibrium trick, right? And okay, so let's go through the statements one by one. So A is saying step 2 as the rate determining steps, all others as fast steps. If we did that, we would get D as in our rate law, but we don't see that. So A is going to be false. B is saying step 1 as the rate determining step, all others as fast steps. And that is valid. We can do that because A and B are reactants for step 1, which matches the rate law, right? So that can work. C is saying step 3 as the rate determining steps, all others as fast steps, not fast equilibrium, nothing. So therefore, we expect just E to be in our rate law, which we don't see. So that's not going to be true either because we trust the experimental data, right? D is saying step 3 as the rate determining step, step 2 is fast equilibrium, and step 1 just a regular fast step. So let's say this is fast equilibrium and this is the slow step. So what that would lead us to is canceling out E, but still ending up with D as our reactant. But again, we don't see that. Sorry. We don't see that in our rate law. So that is not going to be true. And then finally, E is saying step 2 is the rate determining step and step 1 as the fast equilibrium step, while step 3 is the fast step. Okay, so if this was the slow step and this was fast equilibrium, it's also fast, but that doesn't matter if it's not in equilibrium. Then we can directly relate step 1 and step 2. We can cross off D, and then our total reaction would look like this, simplified, which is reflective in our rate law, right? We have A and B. Okay, so that would be true. Any questions on this one? Okay, for 10, we are naming the Newman projection here. Again, first thing you always want to do is draw it. And so I'm going to color code everything here so it's nice and clear. So this dot here is going to be my first carbon that I'm looking at. And then we can do green is our backward carbon. There is some bonds that we can't see between these. And let's just label what's coming off of each of these. Off of the red carbon, we see an ethyl, hydrogen, and methyl. So we have an ethyl, hydrogen, and methyl group. Off of the green carbon, we have a hydrogen, an ethyl, and a sec-butyl. Okay, so I recommend brushing up a little bit on your nomenclature. So we have a hydrogen, ethyl, and sec-butyl. Okay, now again, this is a really ugly molecule, hard to interpret. And so I like rewriting this or redrawing it in a way that I can easily name. So that's what you should get. And try to find the longest chain with the most substituents. If you do that, you should get, I believe, this chain. And because this is symmetrical, it doesn't matter which way you start from. And so you should get 1, 2, 3, 4 ethyl. 1, 2, 3, 5, 3, 5 dimethyl. And then there's a total of 1, 2, 3, 4, 5, 6, 7 heptane. Okay. Any questions on my process here? I looked at the Newman projection, translated it to kind of an ugly molecule here, but it made sense because I could see what's coming off of each carbon. And then I redrew it so it's easier to interpret. Okay. And then 11 is looking at half-life. We've done similar problems. So here, it'll always be in a very similar format like this. We have 0.5 hours, where the concentration goes from this to this in the same amount of time. So basically, you start out with 1.9. It decreases by half in 0.576 hours. In another 5.567 hours, it decreases by half again. So we know that's the half-life and it's not changing. So we should be remembering our first order reaction. Okay. And it's saying if you set up another experiment, how long will it take for 0.32 molar of Tylenol to reach this amount. So we're thinking time here. We're thinking integrated rate law. Okay. And the first thing you should do is kind of write out what is the half-life equation for first order. And it's always going to be equal to ln 2 over k. And here we know that our half-life is 0.576 hours. And our k we don't know. So we're going to solve for k. So step 1, solve k. Okay. And once you solve this, k should equal to 1.203. And we can do a lot with this k because we need to include it in our integrated rate law here. Okay. I know we're dealing with integrated rate laws because we see a change in concentration and it has to do with time. And so the integrated rate law for first order reactions are ln of our final concentration equals negative k t for time plus ln of the initial concentration. Here our final concentration is 0.0709. Our initial concentration is 0.327. Our time is what we're searching for. And k we solved in our first step. Okay, and once you put this all together, it'll allow you to solve for time, which should be 1.269 hours. Okay, so just to reiterate, first step was to solve for k after recognizing what order this reaction is, and then the second step would be to use the integrated rate law to find out what is the time that it takes for this concentration change. Okay. Any questions on this one? Okay, and then the last one is RNS configurations. So this is a little bit trickier, I guess. So I think this is actually straight out of my Orgo exam when I took it. So this stuff will never go away. I'm just kidding. If you're taking Orgo, this stuff is pretty important. And this last part of the class is really, really, really good introduction. And it'll help you a lot on the first exam for Orgo if you're taking it. Okay. So we can start out with this one. Actually, we'll start out with the X carbon because that's how I wrote it here. Okay, so we have a methyl group here. We also have a hydrogen group that we can't see because I didn't write it in because it is assumed. And it's in the back, so where it's supposed to be. Okay, and now we just need to start assigning priorities. Automatically, I know that sulfur is going to be number 1 because it is a higher atomic number than anything else here. And we know that hydrogen is going to be number 4, so we have to figure out 2 and 3. Okay, our options are this route here or this route here. Okay, if I go here to the methyl group, it's a dead end, right? It's a dead end, and we just reach hydrogens and that's it. However, if we go this way, we're just going to keep hitting carbons and carbons and eventually hit this nitrogen and eventually hit this sulfur. And so that's how we know that this is going to be second priority. This one will be third priority. And then when we connect everything together, we'll go 1, 2, 3. And this is going in the counterclockwise, so this will be S, okay? And the hydrogen is where it's supposed to be, so that's all good. And then on the other carbon, we see there should be a wedged hydrogen here. The reason I know that is because there's a dashed nitrogen. And so there must be another hydrogen that is wedged automatically I know that's going to be fourth priority. I also know that this nitrogen is going to be first priority because we're comparing it against carbons here. Now, all we have to deal with is figuring out the configuration or the priority between these two carbons. And so they'll kind of like have a race to which one hits the higher priority group first. If we go on the bottom direction here, we're going to hit a carbon, and then we're going to hit a sulfur. So we're going to hit a sulfur in 1, 2, 3 steps. Okay, 3 steps. If we go the other way over here, we're going to hit that carbon in the same amount of steps. So 1, 2, 3 steps, we're at the same spot, and that's not helpful. What is helpful is branching out in different directions. So if we go this way, then we'll also branch out eventually this way into reaching this sulfur. However, if we just go this way, the only other way to branch out is on the methyl group, which we know it doesn't have very much value. It's going to hit a dead end, and that's that. But on the top left side here, we hit a sulfur. Okay, it's like a gold mine, and so we're going to label this carbon here as second priority, and this one is going to be third priority. So when we connect everything together, so 1, 2, 3, this is going clockwise. So this will be R. However, we're not done yet because our hydrogen is in the wrong position. Our lowest priority group is not in the back, it's in the front. And so all we need to do is just switch this into S, okay? So both of these configurations end up being S, okay? And so then C is the answer. Okay, so that is everything.